Okay, hopefully you're seeing the right thing. So yeah, I guess let's just jump in. Here's a quick overview of what we're gonna cover today. So to start off with, Silvio and I'll give a high-level introduction of data analysis in Viz and introduce some of the topics we're going to talk about today. After that, John, who you heard from a little bit already, is going to talk about V&D and other molecular dynamics type visualization and computation. Then we'll take a break. We have Dan Lipsa from Kitware will come in and give a presentation and some hands-on stuff with ParaView. And then after a break for lunch, Cyrus Harrison from Lawrence Livermore, who's part of the Visit team, one of the main developers there, will come in and do a similar hands-on and overview of Visit. So if you haven't already, there's links in the Viz Slack channel with pointers to where you can get the software and data sets that will be used for those sessions a bit later. And then Scott Pierce from UCAR is here, and he's going to talk to us about Vapor, which is a visualization application that's well, has some of the same characteristics of some of the other applications. It's geared more towards specific domain science in the geosciences. And then we'll have another break, and then we'll wrap up the day with a handful of presentations on doing some Viz work and other things with Jupyter Notebooks. And for that, we have Tommy Marinan, who's from St. Thomas and Argonne, along with Dave Cope, who's from NIU, and Cyrus again, and Matt Larson, who are both from Lawrence Livermore. Okay, so that's sort of an overview of the day. So here's a high-level plan for the next 45 minutes as part of this little intro we're going to do. So I'll start with showing some examples of visualizations that our team has done, working with large data science data. Talk a little bit about visualization resources that are available. I suspect you've used Cooley already a little bit. Talk about Viz tools and formats. The bulk of the time that I'll talk about different types of data representation. So things you can be thinking about in terms of how you want to represent your data in different ways of doing that. Briefly, a couple of slides on using visualization for debugging and other purposes beyond just sort of the actual data exploration. And then at that point, I'll turn it over to Silvio, and he's going to talk about in situ viz and analysis. And if you're not familiar with that, he'll tell you more about what that is later. I'll probably allude to it a bit in the slides I'm going to talk about, but Silvio will dive in a little bit deeper than that. So here's a few examples of some of his cases, and this is one that's actually pretty old, quite a few years old now, but it's one that I like to share because it's a good example of multi-scale visualization and simulation. In this case, what we're looking at here is arteries in the brain, and in particular, what they're interested in is this balloon structure that's basically it's an aneurysm on the wall of one of the arteries, and in particular, they're interested in how the performance or the things that happen in the overview, the full structure. And here you see these swirly lines that are part of a fluid dynamics simulation, how those things and flow throughout the whole system, in particular, impact what's happening in this aneurysm. And in particular, they're looking at these particles that blood platelets that pile up potentially on a area on the end of the aneurysm that could cause the aneurysm to burst or to have a clot break free and cause an obstruction. And so, as I said, it's a multi-scale problem. So they're coupling two codes to fluid dynamics for the large scale flow, and then a particle dynamics code for the individual blood platelets. And so they're run at very different scales and take different amounts of compute. And so the fluid dynamics code, again, this is a few years old, so it ran on one of our previous machines. It ran on one rack of that machine. So on the order of 17,000 processors. And then the particle dynamics in this small subregion, I'm assuming you can see my mouse, right, in this small subdomain at the end of the aneurysm, the particle dynamics code ran on 31 racks of machine, right? And so there's no way that you can do that level of detail, that level of granularity throughout the whole system. And so it's important to be able to couple these two codes that talk to each other, and it's coupled both ways. So they both, the fluid impacts the movement of the particles, the buildup of the particles on the wall of the aneurysm impact how the flow moves through the region. And so there's inherent challenges with that, not only with the simulation, but also with the visualization, because the scale, physical scale is on greatly different, very dynamic range of domains. So that's one example of some viz that we've done. And here's another. This is simulation of massive stars, which can be as much as 100 times larger than our sun, which is approaching sort of theoretical limit of how large stars can get. And despite intense gravity that these stars have, they produce large outbursts of gas, resulting in loss of mass. So that was one of the goals of this project, was to understand how that happens. So this is an example of one of the cases where, in addition to research universities and other domain, other national labs that use the ALCF resources, we also work with a number of corporate partners as well. This is an example from TEA Technologies, where they're building devices for magnetic confinement that's looking into the use of plasma and fuel fusion. A few examples of material science, molecular type simulations and visualization. These are all examples that were done using VMD, which John will talk a lot more about coming up. And then one last one. This is from the HACK team, who does dark matter simulations. So what we're looking at here is evolution of the universe, and these big clumps are bright regions, or these clusters of particles where there's on the order of tens of thousands of galaxies are forming. So a little bit about Cooley, which again you may have already used a little bit last week. It's our analytics and visualization cluster. So it's outfitted with I'll say higher end GPUs. They're quite a few years old now. We're actually in the process now of looking at a replacement resource, which we're still hoping to get on the ground this calendar year. We'll see how that goes. But at any rate, it's a 126 node x86 cluster. One of its advantages is it does have a lot of memory, so 384 gigs per node. And importantly, it shares file system. It mounts all of the parallel file systems. In addition to the data file system, also Eagle and Gran, which are our shared file systems, which you may have already heard about. Right, and so that's important for not, if you're going to be doing post-production visualization, you don't want to have to move data around. So being able to access the data where it lives is important. And it also shares a network with data as well. So a little bit about some visualization tools and data formats. So there's all sorts of tools out there for doing viz. This is not by any means an exhaustive list, but some examples. And there's, so for example, there's visualization applications, but there's also APIs and some that are geared, that have take advantage of the GPU and that sort of thing. So Visit and ParaView and Insight are sort of some of the standard in the field open source. Well, I should say, so Visit and ParaView are open source. Insight is a commercial product, but these are general purpose applications. I'll talk a little bit more about those in a second. In terms of using some of these tools this week, Visit and ParaView are both available on both Cooley and Theta. There's other tools that are more domain specific. As I mentioned, VMD, you'll hear more about from John, and Vapor, some more this afternoon from Scott. There's APIs like the Visualization Toolkit, VTK, which some of the other things are built on top of. ITK is another for doing segmentation and registration. I mentioned, some that are geared for GPU performance. So we have a OpenGL shader-based application that we use in a house that's geared for doing volume and particle rendering. Lots of analysis tools, MATLAB, Parallel R, and other utilities as well. And as I mentioned, this is not by any means an exhaustive list, but just some examples. So a little more detail about the Visit versus ParaView versus VTK. So as I mentioned, VTK, the Visualization Toolkit, is a programming environment or API. So some of the other tools are sort of built on top of that and abstract away some of the complexity. And so ParaView and Visit are really general purpose end user applications, but they're designed to be parallel and distributed so that they can take advantage of running in parallel and really make use of scalable resources. And as I mentioned, they're general purpose applications that are GUI based, so are largely GUI based. So there's a front end that you can use to establish your pipelines and load up data and apply different algorithms and such. They have this client server model that I mentioned, right? So this supports remote visualization that enables you to use the HPC resources for doing all the heavy lifting, and then you have a lightweight client that runs locally, and you'll see some hands-on examples of that in a bit. They're both scriptable and extendable, right? So hopefully you don't hear all this background noise, and I apologize. I'm close to the laundry, and it's being very loud at the moment, so hopefully you don't hear it. It's scriptable and extendable. So one of our typical mode of operation is we'll use the client, the interactive client, to set up our pipelines, load up data, figure out what the visualization we want to do exploration, and then save those as scripts and do some additional scripting, and then run those same scripts on either larger data sets or on a time series of data, and run those in batch. And again, as I mentioned, it's extensible, so you can write plugins for if you need to load data types that are not natively supported, largely built on top of VTK. And they do also have in situ capabilities, which essentially is, because data, the rate at which we can write data to disk, right, is we can't write data as fast as we can compute it, so you end up losing a lot of data. So there's been a big push in the community for doing in situ visit analysis, which enables you to look at that data while it's still in memory, so you don't have to throw it away. And again, Silvio will talk much more about that in a bit. So those are largely built on, as I said, VTK, which has some additional capabilities, finer control, and a smaller memory footprint, but also requires more expertise. So you're largely building custom applications, or, for example, writing custom plugins for one of these other tools. So there's lots of data formats out there. Again, this is by no means an exhaustive list. Just an example, and it's probably, I'm sure it's grown much since I last made this slide. But chances are there's probably a reader for whatever data format your simulation code is using. And if not, that's where the plugin and extensible capabilities come in, where you can essentially write a plugin to read your data into a format, essentially VTK, that visit impaired will understand. All right, so now I'm going to switch over, talk a little bit more about specifically about different types of representations for representing what your data looks like, right? So largely in large scale simulations, the data has some inherent physical representation, and so how do we visualize some of those things, represent it? So volume rendering is one of the often used visualization techniques. There's lots of different algorithms for doing this, but basically it's you have a 3D volume of data, and you shoot rays through that volume and trace along that ray, and whenever you intersect with the data point in the data set, you basically have a lookup table, look up the value that sample in the data, and look that up and use a color table and a transfer function, which maps that value to a color value and a transparency. So the transfer function is what says what the opacity is. So if it's depending on the transfer function, right? If it's you could say that a particular value in the data set is more opaque or more transparent based on this transfer function. And so for some of these examples, for example, if you look at a little mouse friend there, you can define different ranges of values to be different colors and different transparencies. So for example, this is essentially a density map, and we know that the density of bone is in a particular value range, and so you can set the values in that range that map the bone to be a particular color and opacity. Same goes for different types of tissue and muscle, cartilage, etc. And so similar in some of these other views, right? We know that particular values are within a particular data range, and so we can set color and opacity appropriately to represent this. Other representation is the use of glyphs, which is essentially a 2D or 3D geometric object that represents a data point. And so the location is dictated by its coordinate, right? So it has some Cartesian position within the data set. And then you use different other attributes of the data to dictate attributes of the graphical entity. So for example, color, right? So for example, in this image on the top right, we have a bunch of particles in a fuel injection into an engine simulation, And so the color is based on the particle's velocity. And so higher velocity as they're being ejected from the fuel injector. And so they start out red, and then as they dissipate and slow down, they go to yellow. In the case of this middle one here, we're actually encoding a number of different variables, right? There's a vector that represents the direction of velocity in this case, and so these arrows are oriented based on the direction of the velocity, and then they're scaled and colored by the magnitude of that velocity. So contours or isosurfaces, isocontours are called a number of different things. So this is a 2D, in 2D it's a line, in 3D it's a surface, and it represents a constant value. So essentially everywhere where the variable that you're looking at is the same value, we create a surface in 3D. And looking at how you can do these things, Visit and Pair View are good at this. VTK again, also good at it. Requires a little more effort, and there's different ways that you can utilize this. So, for example, in this example on the left, there's multiple isosurfaces here, and so each of the different colors, they're colored by the same value as the isosurface. So, right, so there's 4 different surfaces here, and they represent 4 different values in this case. While over on the right, this is a single isosurface, so a single variable or a single value for the value of the surface, but then we're coloring that surface by a second variable within that data set. So there's ways of combining to show to represent multiple values in a single with a single representation. Cutting planes, which or slices, which is exactly what it sounds like. Basically, you take a plane and you slice it through the data set and sample it, the data along that slice, and color it by that variable. Again, Visit and Pair View are good at this. V&D has similar capabilities for particular types of data. So this is useful for seeing, for example, in this case, we're looking at temperature within this combustion chamber, and so looking at actually I forget if this is temperature velocity, but at any rate, you can see the patterns of where the fluid is moving. So there's a couple of different representations that you can use for looking at a vector field for vector data that has multiple components. And for this, essentially you need to have a mesh where there's connectivity. And so in this case, we're looking at streamlines, and so streamlines, they show the direction that element travels at a particular point in time. So within a single time step of the data, you basically start with a bunch of seed points at some specified location within the mesh, and then you look at the vector at each of those seed points and say, okay, what's the magnitude and direction of this vector in the field, and essentially follow the path that would take within a time step. And so that reveals things like in this aneurysm, sort of the complexity of the flow within the aneurysm. This one here at the bottom is an exploding star, and so there's the circular rotational pattern in the flow that's happening, and so this is looking at that flow essentially within a single time step. Additionally, you could have, you could represent it as path lines. And in this case, it's similar in that you need a vector field that has some connectivity on a mesh. But in this case, we're actually looking at data over time. And so we're, instead of saying tracing the path within that single time step, you take a particle, eject it to the next position on the mesh, and then look that up, look at that position in the next time step, and then repeat that process. And so here we're showing the particles as they move through the domain, and we're drawing little trails here that show the path that they've taken over the past n number of time steps. And I apologize, I'm going to pause for 1 second. Sorry about that. It was getting very loud here. So this is looking at just showing how different types of some tools are for doing work in specific domains. And so in this case, molecular dynamics is, again, there's a number of tools for doing this type of thing. But in this case, there's representations that are specific to the types of domains that you're looking at. Again, John will talk more about VMT up next. Again, visit specifically for molecular type of data. Visit and peer review have some support for this. It's improving all the time, but again, looking at tools like VMD, Vito, those types of things that are domain specific, that have support for tools for representations that are specific to different types of science domains. Okay, so a couple more just quickly before we, if I pass it on to Silvio. So beyond just doing the initial data exploration and using visualization for essentially the final step of your pipeline and communicating the results of simulations to folks, whether it's to the science team or to the general public or whatnot. There's other uses of visualization, and I like to show this example. This is actually the same code, the fluid dynamics code that was used for the blood flow stuff that I showed at the beginning. And here we're using visualization for debugging. And so this is an example of two marine propellers, and you'll see in a second as I once I advance on this, that these two propellers are rotating in opposite directions. So fluid is moving from right to left. And so keep your eye on this propeller on the right, which is essentially the front propeller. As the simulation progresses, and these two propellers are rotating in opposite directions. But eventually, the front propeller disappears altogether. So as you might expect, they were getting results that didn't make sense, because as the second propeller was removed from the longer in fluid flow, and so they were getting results that were totally different from what they were expecting, right? And so because they were getting these results they weren't expecting, they asked me to help visualize, and in the process of that, that's how we discovered that there was some bug in their code where there was some variable that wasn't being reinitialized or something, and that caused that propeller to go away. And so this is an example of how visualization can help you not just understand the final results, but help identify places in your code there might be problems. And so here's an example. Here's what essentially they were expecting to see. You can kind of see, you see this little bit of white here. So underneath here is where those propellers are. And so they were expecting to see these these vortex structures as the simulation progressed. But again, since there was one of these propellers was missing, this looked very different. They weren't getting the results that they expected. So just one more quick example of using Viz for diagnostics, right? And understanding how code is performing, for example. And so this is a case where, so this is a volume visualization using our homegrown software. And essentially, right, so you look up data you cast rays into this data set, and where you intersect the data set, you look up its value, right, and color it based on the value that you find in the place, that you intersect, right? And so we were looking to optimize this code and parallelize it a little bit further than it already was by adding threads. And so we wanted to understand better how things were performing. And so we made a switch in the code. Instead of looking up the value where we intersected the data, we colored it by the thread ID of the process that was looking up the data in that location. And so you can see by changing the way that we laid out the threads, you get a very different layout of. And so this is essentially showing the memory layout of how the threads were acting on the data, computing. And so I don't remember off the top of my head which one of these turned out to be the most optimal, but you can see that there's 4 very different implementations or arrangements. And so based on this, we were able to identify the optimal way to lay out the threads in the process. Okay. And so with that, I'm going to turn things over to Silvio, who's going to talk about in situ viz now.
Thanks, Joe. And while I put my slides up, there's a question on chat asking what's the difference between streamlines and the path lines data visualization.
Yeah, great question. So the main difference is that streamlines, you trace the path of that particle within one time step, and so you're not changing time. With path lines, the idea is that you trace the path. You start with in one time step, you evac that particle, right? You see how far it's traveled, and then to the new location, and then you look up that location in the next time step rather than the same time step. And so you're looking at the path a particle takes over time rather than within a single time step. Does that help? Nope. All right, and I think those are your slides now, right? That we're seeing.
Yeah, these are my slides, and I'm not seeing the chat anymore. So if there's something pop up on chat, feel free to.
Yeah. So that was yes. Yeah. So we're good to go.
Okay, good. So we'll transition to the final 10-15 minutes talking about in situ viz and analysis. And Joe already gave some of the motivations for this. So traditionally, we've done in viz and analysis, we have this workflow that is called post hoc viz and analysis, where the big simulations run. They save a lot of data on this, and sometime later, the visualization team will come and create some visualization from the data that was saved. Now, with exascale simulations in the horizon, they're already here. The amount of data that these simulations are going to generate will be enormous. And it's not possible to save all that data, right? So our community, the viz and analysis community, has been thinking of solutions for this, and now for quite a few years, probably a decade now. And so we're going to try to give you some of the tools available for this now. And this slide that I'm borrowing from Ken Moreland, and it's already an old slide, right? So it's showing that there are 5 orders of magnitude differences between the compute and I/O, right? So 2 orders of magnitude and going from compute to node memory, another 2 orders of magnitude when hitting the interconnect, and 1 more order of magnitude going to storage. So that's a lot, right? And the flops, the computational capabilities increasing, right? Much more faster than this. So this gap, in fact, the fact between flops and I/O is increasing. It keeps increasing, right? So those are the main motivations for looking at doing in situ based analysis. And essentially, in situ means that we run the visualization algorithms while the simulation is running, while the data is available in memory. And that gives us additional opportunities to look at more data, right? So there's no need to, if this works as expected, there's no need to save the data now. And we have access to the full data sets, not extracts. And we have access to the all the time steps, not something that you save every 10 time steps, 100 time steps, because you're limited on disk and storage, or I/O is too slow for saving that. So with that, we're addressing also this important point about lost science, right? So hopefully, if you have the entire data set to visualize or analyze, you will be able to capture things that may be lost if you were saving some subset of the entire data set to this. So that is the main motivation of in situ based analysis. So with that, I would like to describe 2 frameworks, and I'll start by saying that there are many in situ based analysis frameworks. These are the ones that we support at ALCF. So if you will be running your codes at ALCF and probably in many other sites, right? Like our sister facility in Oak Ridge, or maybe NERSC, or maybe Livermore, and even the NSF sites, it's likely that this tool set will be supported, right? So I'm mentioning this 2, but with the caveat that there are many others. Right? So we are involved in this project, and we support them. And we can help you instrument your code with either Sensei or Ascent if you're interested in exploring in situ based analysis. So we're trying to compare here the benefits of these 2, right? So Sensei was designed with this premise of write once and run everywhere, where you instrument the code once and use the VDK data model to convert your data to, right, with 0 copy when possible. And you can substitute your analysis. You can plug and play your different analysis backends. And that's the idea. So just with a simulation that is instrumented, you can plug in visit or the in situ component of visit that is called LiveSim. Catalyst, the in situ component of Fairview, you can plug some Python algorithms and many other different backends, right? There's also Adios for saving data, or for moving data through the network to a different resource, and maybe we'll talk more about that. That is a different way of doing things that we call in transit, right? And there, I covered all the number of backends. So let's move on to Ascent. And Ascent was designed mostly as trying to be a framework that is really lightweight, right? Minimizing a number the dependencies on the code. And we'll talk more about that at the end of this presentation. For data model, it uses Conduit, from Livermore, and Matt and Cyrus are here and will presenting later today. So they are experts on this. They are the ones, the main developers of Ascent. So if you have questions, very specific questions about Ascent, feel free to talk to them. And it uses VTKM for implementing algorithms. VTKM is the framework, the evolution of the VIS algorithms in BTK to try to use the intranode parallelism that you get on accelerators, right? So this tries to show, and the idea that we want to convey here is that instrumenting and simulation code should be simple, right? So on the left, you see that on black, that represents the original simulation code, right? There's usually an initialization in step one. There's a loop for computing every new time step. And then there's a call to finalize the simulation and close everything gracefully. So when you instrument the code with Sensei, you also insert an initialization for something that is called the bridge in Sensei, and that's what interfaces the simulation with the vision analysis code. And then in every new time step, when there's new data, you call execute. The bridge refreshes the view of the data on the analysis side. Prior to finalizing the simulation, you call a bridge finalize that will take care of closing everything on the in situ side. Now, if you look at Ascent on the right, there's a number of very similar calls, and it is very similar, or pretty much the same instrumenting and application with Ascent, right? Except that the data models are different. Now, as I said, we're a small community here. The in-situ vision community is really small, and we work together on multiple projects, right? Not only in-situ vision analysis. So as a result of this, the Sensei and Ascent projects have a joint tutorial at SC. We had that tutorial in 19 and 2020. And this year, we also have it confirmed. So I will be there, Matt and Cyrus will be there. So if you're interested in these topics, feel free to attend this tutorial at SC21. Since this is ATPESC is part of the exascale computing project, I wanted to show this slide showing how all these technologies fit together in this scheme, right? So the Alpine project includes Ascent as its main technology, and also includes the LiveSim library in Visit and the Catalyst library from ParaView. It also includes Cinema to extract and create output and artifacts, and underlying it, there's VTKM for implementation of all the algorithms. I should also say that Sensei is part of this now as part of the ECP data and Viz SDK. So everything converges. And here's a quick slide about VTK that I'm gonna skip. You will have it because I'm running out of time. There's also a quick reference to Cinema, and this is really important. This is about generating in situ image databases rather than saving the huge data, the huge raw data set, right? You could create a multiple views of the data in different angles that you will expect will be useful for later exploration, and with different values, for example, of isosurfaces that you can explore later, right? So this Cinema defines how to do that, and it specifies how to create those databases that you can interactively explore after the simulation finishes. And it's integrated with ParaView and Visit and Ascent. Now, one final thing that I would like to mention is that things are changing, right? So Catalyst recently has a new iteration, right, or 2.0 revision. And they're trying to address some of the issues that we've observed in the last few years, right? Some of those issues are that sometimes instrumenting your code for in situ baseline analysis requires a number linking with a number of external libraries, like VTK, for example. VTK is huge. Understandably, science teams and simulation codes don't want this, right? They don't want to link. They want to be as much. They want independence of this specific libraries, right? So this is what Catalyst 2.0 is trying to address: external libraries, complexity in the VTK data model. So they're trying to switch things, change those things. So for example, Catalyst 2.0 adopted Conduit, the one in Ascent, right, from Livermore. And that simplifies the description of the data model, and at the same time provides a zero copy. And now they also inspired by the ABI specification that, for example, MPitch uses, that allows you to substitute MPIs from different vendors, right? It does the same. It tries to do the same and so you instrument the code link with a stub library, very simple, that they provide. And then at runtime, you substitute that with the Catalyst library. So there's a paper here, the very recent paper presented at WOIF, which is a workshop in ISC. So reach out. I don't think it's online, but if you reach out to the authors and are interested in this, they will be happy to share a copy of this paper. Now, with that, a final remark here. If you're running at ALCF and if you're a user of our resources, feel free to reach out for help. You can email support@alcf.inl.gov, and we can help you with anything related to this, including publications and production-ready animations and pictures for journals. So here you can see examples of journal covers that our team has produced. And with that, I'll stop here. Hopefully didn't run too much over my time. And these are the emails of our entire visualization team at Argonne. So feel free to reach out with questions.